I'm grateful to Kirill for another invitation. It's my fourth time, I think, in Nottingham. And yes, this subject is new to me also. I'm not an expert in this, so you will please excuse me if I won't be able to answer all your questions, so especially deep questions, which I perhaps would not be able to answer. So I was just fascinated by this subject a while ago and started learning it, and then I communicated something to Kirill, and Kirill suggested that I should speak on this issue today. So the issue is finite, as you see, perturbative quantum field theory. It's an approach to quantum field theory which is not quite new, but it's probably not well known among the community. Perhaps not all the people are aware of its existence. And it's for this reason that it would be perhaps interesting for you to learn something about it. And as for its practical, usefulness, for example, I'm not quite sure whether it's useful in practical calculations in quantum field theory, because it doesn't produce any results thus far, at least, which would be different from the usual perturbative quantum field theory. But from the conceptual point of view, I think it's useful that we know about its existence, and maybe it will, hinder us into some direction in the development of quantum field theory, which would make it completely finite without any extra dimensions or superstring theory and things like that. Okay?
Why didn't it catch on?
Sorry?
Why hasn't it caught on?
Why didn't?
Why?
Well,
it probably hasn't caught on. Why is it being forgotten, I guess?
It's not forgotten, it's just not popular among, there are several people who are working on it. Quite a few people who are working on it, but I think it's because it doesn't give you any practical differences from the original quantum field theory, perturbative quantum field theory. And I will explain that, I hope.
So it is sort of manifestly finite without
yes. Yeah, it will be finite, yes, with renormalizations, with finite renormalizations. So it's an ideological framework which I'm going to discuss. Purely ideological, philosophical even, if you like, but maybe not very practical. Okay, so many of you, if not all, you know that in calculating perturbative series in quantum field theory, you encounter with the so-called ultraviolet divergences, like the second graph, which describes scattering of two particles. Yes, has a loop here involved, right? And if you calculate this integral, it diverges. So normally, when a student studies quantum field theory, he's been told that he's dealing with perturbation theory, but now the second term of that theory becomes infinite, and you have to do something about it, making it finite, regularizing it, and that creates a lot of confusion. At least for me, it created a lot of confusion when I thought about it. So how could you trust perturbation theory if the second term is divergent, formally infinite? And the second question is, why, in spite of that, quantum field theory works so well, at least in the models which we know and have tested thus far, like QED, for example, right? So that's the question. Next issues which are related to this divergences problem are the so-called naturalness issues, like, for example, if you calculate the contribution to the mass term, to the mass of a scalar particle. This will be all scalar particles here, right? I will illustrate the theory with purely lambda 4 scalar field theory to avoid unnecessary complications involved with in connection with spin and etc. So if you calculate the contribution to the mass term using this graph, it is quadratically divergent, as we know. Yes, if you are using some kind of cutoff, right, and you think it's extremely high, this cutoff is denoted by lambda here, so you get a radiative contribution to the mass squared term, which, if you want your particle to be light enough, like if you want to describe the Higgs boson, for example, then you should say that you have a counter term or a bare mass, if you wish, yes, which cancels this extremely high contribution. up to a small amount which is remains. So this is kind of naturalness problem or fine-tuning problem or mass hierarchy problem, one way of stating it. And the same problem appears if you want to calculate the vacuum energy by using the loop graphs, right? So you have divergences which go like lambda 4, which gives contribution to cosmological constant, and then you have to subtract it with some Bayer coupling or...
What about quadratically divergent graph? You mean this one on the left, kind of in the middle on the left? Is it the one you mean?
This is quadratically divergent, and this is fourth order, sorry. This is fourth order divergent, the last one. Diverges like lambda to 4 if lambda is your cutoff. Okay, I should move faster. Now, what is the nature of these divergences? Of course, we know that in momentum space it's because our momentum integrals diverge in the ultraviolets. So Bogolyubov in 1952, he was thinking about this problem. He paid attention that in the coordinate space, if you're thinking about the coordinate space representation of the scattering matrix or Feynman graphs, the divergence arises because you're trying to multiply two functions with the same argument here. Like these are two Feynman propagators depending on the same argument, but these functions are not usual functions. These are distributions, what we now call distributions. At those times, the theory of distributions was only beginning to be developed, I mean, taking its modern frame, I would say. So yes, because Lawrence Schwartz has just in this same year, I think, has published his volumes in which he gave a complete theory of distributions. So now you're trying to multiply two distributions, and this is just a not well-defined operation, a simply undefined operation. So what a physicist or a mathematical physicist would try to do, and what is usually done in this case, yes? You try to define this product. So you go to momentum space, you make a Fourier transform of each of the terms, and you try to form a convolution of these Fourier transforms. So if this convolution exists, then you can declare it to be the Fourier transform of your product. You make inverse Fourier transform, and you get your product well defined. In this case of Feynman propagators, it's clearly, the convolution is not defined. You take a convolution and you see that it's ultraviolet divergent on the high momenta, so you cannot think of this product as a well-defined distribution. And that's the problem that a physicist is struggling with when he makes all this renormalization theory. He tries to replace this product by something finite and well-defined. All right? Now, here is a simple example. For example, you cannot even define the product of delta and theta in this way, which look as rather harmless functions, right? Because if you make a Fourier of both, then Fourier of delta is just constant, Fourier of theta is this function, and you integrate this, and it's ultraviolet divergent. So it's an instance of this issue here. But now the question is, do such products of the Feynman propagators, the difficulty is that you have products of Feynman propagators, do they appear actually in the quantum field theory? Is there a way of avoiding their appearance, for example? Are they unavoidable in quantum field theory? And the answer is no, they are not unavoidable. And this was really first proved or demonstrated by Epstein and Glaser in 1973. It's a very famous paper. They have shown that the causal approach to quantum field theory developed by Bogolyubov a little bit earlier leads to expressions which are finite in all steps. And you actually don't encounter the nasty things which we encountered before. Sorry?
It's causal. How, in what way is this causal and Feynman's not causal?
Sorry? Causal, I said.
You're sort of stressing that it's causal, that Feynman is causal as well.
Causal quantum field theory, I'll come to that point. It's a causality condition. Well, it's maybe not, it's some consequences of it which will be important, but the causality itself lies in the core of the quantum field theory, so it will play an important role here. So we'll see it later. Yeah, so following this paper there were a number of developments until even recently, so there is a review paper here which you can read about this. this story, and even the books have been written by Günter Scharf. The last edition of Finite Quantum Electrodynamics appeared in 2013, so a couple of years ago. So this is, in some sense, a well-known subject, but not everybody is aware of its existence, right? So I'll start gradually introducing, the necessary notions. The first thing you have to realize that the field operator in quantum field theory is an operator value distribution. It's not specified as an operator at a given specific point x. It's meaningless. If you try to apply it to any member of the Fock space, then it gives you a state with an infinite norm. So it's not well defined. So in order to make an operator out of it, you have to smooth it, integrate it, or so apply it to some test function, f of x, which will always be assumed to be a function in the so-called Schwarz space. So it's a space of functions infinitely differentiable and decreasing faster than any power at infinity, together with all their derivatives. So that's the space for test functions. It's chosen because you can then differentiate it as many times as possible, or making Fourier transform, which is also very important. Now, the field operators squared and cubes, again, these are free. I'm talking about a free field operator. This is just a Klein-Gordon field operator, free field. They're not well defined, but their normal product, the so-called normal products, are well defined as in this sense of operator value distributions. So I'm not going into, details of why these cannot be defined. There is some infinity present there in the phi squared or phi cube at one point. So to remove that infinity, which is a simple infinity, we'll always deal with the normally ordered products. Normal ordered product is the product which places all, this is the creation part of phi and the annihilation part of phi, which places all creation parts to the left, annihilation to the right. There are commutation relations here between these fields, right, and it produces some distribution. Yeah, this is, if you take phi, you obtain this d, which is called Pauli-Wheeler's function. It's decomposable into d plus and d minus, which is positive, negative frequency parts. That will play some important. These functions will play some role in what follows.
Excuse me, commutation relations, it is a lead brackets.
No, it's in operational sense. These are operator value distributions. So you can integrate this expression with, you can integrate this with one test function and this with another test functions, and then take a commutator as an operator in the Fock space. It amounts to integrating these both functions with this d plus, which is number. It's like creation annihilation operator commutation relation, which says that that's, but it's a little bit more complicated because it's a field. Is it okay? Now, there is a weak theorem which will be involved in our construction, which is well known to quantum field physicists. Like you take normally ordered products of monomials, phi is at points x's, phi is at points y, and phi is at points z, etc. You can have more, and then it's expressible as a sum of completely normally ordered products times some contractions between. You should contract between the points in different monomials which are not yet normally ordered, right? And every such contractions gives you precisely the positive frequency part of this Pauli-Wheeler's distribution. Now the point here is that you can take some of these points or all of them to be coinciding. Yes, there is nothing wrong in doing this. You can replace all x's by one x here, all y's by one y, all z's by one z. You will get then, by formally applying this theorem, you will get the products, the powers of d plus to the power of n, or d minus to the power of n if you like, because these functions are actually related. D plus and d minus are related to each other. So these powers of d pluses and d minuses are well defined in the sense explained on the first slide. So you can take it Fourier transforms of each product, then convolution is well defined, and then you take inverse Fourier transform, and you get. Now, in quantum field theory, there is also the chronological, so-called chronological weak theorem, yes, which deals with the chronological ordered products. It runs exactly like this one, except that all the pairings now become chronological pairings, and they give you the Feynman propagators. Okay, so you end up with distributions of these kinds. Feynman propagator to the power of n if you think of these points as coinciding, and this is completely not well defined. So the chronologically ordered, the chronological weak theorem is actually mathematically erroneous, you may say so, or not defined. If you deal with monomials of phi with at least some power at one point, okay. Yes, absolutely.
It's not the same as this one.
But it goes multiplied by some theta function. Theta function multiplies positive frequency parts, so it's already multiplication of distributions.
So it's the theta function that spoils the.
Yeah. Yes. Well, you can say so. I mean, actually, d plus times d minus is not defined. D plus times d minus is not defined. You can multiply d plus any times you want, but you cannot cross multiply them. Now, what's the Bogoliubov method? Okay, in the Bogoliubov method, you are looking for the scattering operator. The scattering operator takes some state in the Fock space of the free particles, then evolves it, yes, because of at this time some interactions are taking place between these particles, and then you see what happens in the outcome, yes. So now the Bogoliubov method to describe the theory which would be causal, which has causality involved in it, would consists in introducing a special function g, which switches on the interaction and then switches it off. So the g, which is a real valued function between 0 and 1, just tells you it's a function of space-time. Picked up to be, again, infinitely times differentiable, etc., etc. But so it's a test function in some sense. So it's picked up in such a way that it's, for example, it can have bounded support, for example. So it switches on interaction in some region only of space-time. Outside of that region, the fields propagate as free. But you can switch it everywhere with every strength, right? With every strength g. In that way, the scattering operator, scattering matrix, scattering operator becomes a functional of this field g. And you assume that you can expand this functional in powers of g, like this. So this is again similar to introducing some kind of a distribution which takes g as its argument and produces some operator in the Fock space, which, you know, transforms the initial state into a final state. Yes, these functions t of n are then, of course, their nature is they are just operator value distributions of n arguments. And by the symmetry which you can see here, they can be thought of completely symmetric with respect to their arguments, x1 over xn to xn. Now, the task of the quantum field theory is just to find all this t. Of course, this is a formal theories expression. We are sure even that it's not convergent, perhaps, yes, but it can be taken as an asymptotic series in a quantum field theory. I will be concerned only in these particular terms, Tn, yes, in this series, which in usual quantum field theory, when you calculate them, you encounter divergences. Here you should be able to find all these terms as being finite. The whole series may diverge, of course. It may be only asymptotic. So the causality principle states that if you have, if switch on interaction with a function which is the sum of g1 plus g2, and the support of g2 lies in the causal path of g1, then the scattering operator is just a product of sg1 times sg2. It's as if you are evolving the state from going from the past. First you interact with G1, which is here, supported here, and then you switch on interaction with the function G2, which is supported here. Clearly you will have the product of these scattering operators. Now, so this symbol implies that the support of G2, any set lies in the causal future of the set on the right hand side. So this causality principles gives a very powerful relation on these coefficients, yes, distributional coefficients. And this relation says that if the number of your n arguments are split into two subsets, and one of which is lying completely to the causal future of another one, then this the T of order n is expressible as the product of T of lowest order. First you take T with arguments with m arguments which are lying to the future of the rest, and then T, the rest of the arguments, is tending to the right. So that's the causality principle, and in principle this relation it allows you to calculate Tn recursively, starting from the first order element of the scattering matrix T1, which is usually regarded as the interaction Lagrangian of interaction. Okay. For example, you have given some T1 of x in some field theory. Let it be T1 will be quickly lambda phi to 4 in our case, but normally ordered. And then if you want to find the next order term in the scattering matrix, then you know that it's given by the product T1 of x, T1 of y, if x lies to the future of y, and vice versa. Therefore, this relation already determines you T2 everywhere in the space as a distribution, as a operator value distribution, everywhere except for the domain where x equal to y. This is called a diagonal. So there you don't know this distribution on this diagonal, but you know it everywhere. And you know, and you are sure that everywhere it is finite, because all this this is a direct product of distributions are always finite.
About x on the null code, null related to y.
It is, yeah, it is defined here. Yeah. Because, well, it's the causal future, because well, I don't see any problem here, see, because it's a causal future of if x lies on the light cone of y, it's still in the causal future. So that region is taken care of by this product of two. So suppose you have a test function there, some test function with argument y lying near the origin of coordinates, another line somewhere encompassing the light cone, right? So you simply take t of x with one test function, t of y with another test function, and you don't get any, you have the product of these operators which will be well defined everywhere. Actually, it's a question of, no, okay, I will not perhaps try to figure out why is this the case, but this is the case. There is no problem lying there. The problem is lying on the coincidence diagonal. Okay, so this relation determines it everywhere. Of course, these relations, x to the future of y and y to the future of x, they have the domain of intersection, which is when x and y are space-like separated. In this domain of intersection, the answer for T2 should be the same, whether we calculate it as Tx times Ty or Ty times Tx, because they're both equal here. And therefore, this T should commute wherever the points x and y are space-like separated. This gives you some restriction on the kind of operator which you can have, yes, but in local quantum field theory, this is usually the case. Like in this kind of theory, this condition will be usually the case, and this is trivial. So now the problem is to extend this to the diagonal. Let's see how it works for lambda phi to fourth. Okay. So we're constructing T2, the next order term for lambda phi to fourth. Okay. If x is to the future of y, then it's given by this product. And then you have product of normally ordered fields, and you use the weak theorem, and you get all this d plus squared, d plus cubed, d plus the fourth, times this field monomial, so to say, yes, normally ordered, and these are well-defined distributions. Now, if you multiply well-defined distributions by field monomials, you get well-defined operator value distribution in quantum field theory. By well-defined, I mean they are defined on a dense subset in the Fock space, so everything is, you can calculate with that. Likewise, if y is to the future of x, you can write down the simple expression for this product. I have written it in terms of d minus because it's just convenient to do this. D minus and d plus are simply related to each other, so we don't have to care about this. Now this determines this function T2 already in the whole domain of x and y except for the diagonal. So now the question is just to extend, the problem is just to extend this T2 operator to this diagonal. Because you can see the general feature of this, these are called coefficient distributions. Functions are that they are translational invariant. They are always translational invariant because in the theory we have it's Poincare invariance here. Well, I haven't mentioned that, but we assume, of course, that Poincare invariant, in particular, it's translational invariant. So it's a function of only one argument, basically, and you have to extend this numerical distribution to the origin of coordinate, basically. These distributions of one argument. And therefore, if you solve this problem, then you have extended your distribution to the whole of space, and you have found the T2, which is divergent in quantum field theory, as we know. So, in usual quantum field theory. Now, what kind of function we have to extend? Let's look at it more carefully. So it's given. So I now introduce these theta functions, which you have mentioned, right? Which are necessary here. So we introduce a theta function. A function. Now it's in this case it's a function in Minkowski space, right, of x. I take it to be scale invariant. I take it to be equal to 1 in some cone which encompasses the light cone. It's just bigger than the light cone, no matter how big. And then it should be equal exactly to 0 in the opposite cone, which encompasses the past light cone. And then between 1 and 0 it should interpolate smoothly in an arbitrary way. So here it's in an arbitrary way interpolating between 0 and 1. The value at the origin is not important for this function. Now, because our distribution is defined in R4 now with origin of coordinates removed. So we have to extend it to this origin of coordinates. So this is our distribution. It's just theta plus. So theta minus, sorry, is just 1 minus theta plus. So it has the opposite relation. It's 0 here and equal to 1 there. So now this is the distribution we have to extend. We should think about it as defined in the space R4 without the origin of coordinates. Okay? It's as such it is still perfectly defined distribution because d plus to the power of n are well defined everywhere, and theta plus is smooth everywhere except for the origin, but we don't consider that point here in our space right now. So the usual formal manipulation would lead you immediately to a wrong result. Like you observe these relations, yes, which tells you that theta plus minus d plus minus is equal to, you can replace the Feynman propagator here, any d by the Feynman propagator. And then you can do this operation n times, and you arrive basically at this relation, Feynman propagator to the power of n. But this is a wrong mathematical manipulation in which you treat distributions as usual functions. So first you think that these relations hold, then you think that this relation basically holds, but the next step is actually is problematic, because in the next step you have to multiply two Feynman propagators, which is not defined procedure. You forget about this, and you continue, you go on, you get this thing. So the right way to do is just to extend this distribution mathematically to the 0 point and see what you get. Now this is a textbook result. After that you can struggle with this. You can renormalize it, subtract infinities, etc. Now I'm sorry, I don't know how much time is left. Half an hour probably.
Try to finish
Quarter two, okay. So the problem that appears here is purely mathematical. I just give you a sketch of it. So we have a distribution f with 0 means that it's defined in the space Rn with origin of coordinates removed, okay, without origin of coordinates. Now this means that it can act on any test function which has support not including the origin of coordinates, right? That's exactly what it means. We have defined it there, and we want to extend it to all test functions which can have support including the origin of coordinates, and that's called an extension of a test function. So clearly, if we extend those test functions to the origin of coordinates, we have a complete solution of our problem for the T2 operator, and then next orders can be treated in a similar way. So first of all, how many solutions can we have? If f1 and f2 are two such extensions, then their difference should be supported at the origin. It can have support only at the origin as distributions. And for such distributions, it's well known that this can be only a linear combination of delta function and its derivative, some finite linear combination. So this is this gives you some non-uniqueness to your extension problem, tak? Yes, we have to fix somehow its non-uniqueness, because we don't want to deal with such a huge arbitrariness involved here. So this is fixed by demanding that the extension of your distribution has the same scaling properties at the origin of coordinates as the original distribution, which was to be extended. The same scaling properties, the same level, the same tendency to singularity, or not exceeding actually that. You don't want to introduce delta functions and with huge number of derivatives that would exceed the singularity of your original wave function, right? Which is a reasonable assumption. So by the way, in usual quantum field theory, this would correspond to the following thing. So suppose you have lambda phi to 4, and you are encountered with infinities. You're trying to add some counter terms, which would cancel your infinities, yes, first of all. But then you can add some other counter terms, right? Like phi to 6, for example, or phi to 7, phi to 8, etc. Finite counter terms. You don't do this usually, right? You don't add counter terms which would increase deform the original Lagrangian, for example, of your theory, right? Unnecessarily. They are not necessary. They're not canceling anything, but you could add them, right, with finite coefficients. So this is basically the same requirement, that you don't add unnecessary things here. All right. So this I won't explain perhaps all these notations. These are multi-index notations used in distributions. So omega is the order of derivatives. A is some multi-index with non-negative integers, etc. So it's just to short down the expressions. Okay, so this number omega to which we can have this freedom of extension should be bounded by some singular order of the original distribution. Now, the singular order of the original distribution is defined as its scaling degree minus number of dimensions in which it lives. So the scaling degree is actually the scaling of distribution as we approach the zero. So how fast it diverges. To get it, you just you make a scaling of your coordinate. You multiply by this scaling lambda to some power s, and you look for the least number of this s for which this goes to 0 as lambda goes to 0. Okay. So, for instance, for a distribution which goes like this, yes, which diverges at the origin of coordinate as x to power minus s, the scaling will be equal exactly to s. But for every distribution, you can introduce the scaling number. It exists for every distribution, and then w is its integer part minus number of dimensions, and it's called the singular order of the distribution. Now, for some examples, you can see the scaling degree is equal to s. In this case,
it's also the mass dimension, right, for this example.
Sorry?
It's also mass dimension for these examples. 1 over x power s.
Actually, mass dimension? Yeah, well, this is mathematics, so x is dimensionless. Everything is dimensionless here, but in principle, yes, you can think about
This is length.
Yeah. In mathematical terms, this omega is just, you see, you can still, even if your distribution is very singular at the origin, so you don't know how to define its action on some arbitrary test function, yes, but still you can define its action on some subset of test functions. So W tells you that these functions have to have all their derivatives up to W equal to 0, and then it is easily extendable in some sense to, well, it's actually on the next slide.
So the scaling degree is a good definition if you have polynomial singularities, right?
The scaling degree is defined like this for any distribution f capital.
And if you have something more divergent than polynomial, then it would just be infinite.
It could be, well, it could be infinite. What we usually encounter are finite expressions, but of course it could be infinite. I think you can see, yeah, you can.
Over infinite, for example,
I don't know. Yeah, usually it's, well, for a delta function, for derivative of a delta function, it's just the number of derivatives. The number of derivatives, this modulus of a. So a delta function has w equal to a, actually, right? The distributions which are important for us, for example, in Minkowski space, d plus minus, have scaling equal to 2 and w equal to 2 minus 4 is minus 2. So they're not very singular. Minus 2 is not very singular. The higher is w, the more singular is your functions. But if you try multiplying them, the singularity increases. Well, now maybe I'll talk, well, pass this as in a sketchy way. So if you have a distribution which you need to extend to the origin of coordinates, if you know that your distribution has singular order w, then there are theorems and explicit constructions which tell you that the extension always exists. First of all, extension always exists. It is unique if this w is less than 0, then your distribution is uniquely extendable to the origin of coordinates. To make this extension, you pick up some function which is equal to 0 in the neighborhood of x equal to 0, equal to 1 outside some ball of radius 1, okay? Then you, what happened? Everything switched off.
It's starting now.
Hmm?
It's starting now.
She'll have to use Blackboard then, probably. So I will talk perhaps, yeah, because so you want to define the action of your distribution on an arbitrary test function, but your test function may not be equal to 0 around origin of coordinates, right? And you don't know what to do. So you first multiply your test function by another auxiliary function, which vanishes at the origin of coordinates and in some neighborhood of it. And then you know how your distribution acts on that. And then this auxiliary function, you make a sequence of them in such a way that they tend to unity everywhere, but always remaining point-wise, of course, always remaining equal to 0 at the origin of coordinates. So you take this test function and you just scale it with 2 to the power of I. So if I goes to infinity, it makes this function to become unity everywhere. It shrinks the region where it's equal to 0. In this way, and then this limit defines you the extension of a distribution uniquely. If your omega of your function, the singular order, is larger or equal than 0, then before doing this limiting procedure, you also have to project your test function to the subspace of test functions which have vanishing derivatives up to order omega inclusively. Yes, it's done with another auxiliary function w here, but the result of extension does not depend on this w actually, because it's kind of determined by arbitrary constants anyway. We know about that. It's determined by an arbitrary constant c. So any function would do the same job. So you pick any of them and you do this job. Okay. So the extension is determined by this function, and this number of constants c, which give you just the delta function and its derivative up to order w here. All right. And that's the solution of our problem of extension, and it is finite. There is nothing infinite here, except for some new constants appear here, which are finite. Well, usually we work in momentum space. It's not difficult to transform everything to momentum space, but just taking the Fourier transforms. Every distribution has a well-defined Fourier transform, so you just consistently make a Fourier transform. And the answer in Fourier transform of the extension problem looks like this. So you have f0 which you want to extend, you multiply it by this auxiliary function, make a sequence of it, then you get a sequence of functions fi which now can act on any test function. You project your test function, etc. So in Fourier transform you just take a Fourier transform of this fi, then you should subtract some polynomial in k-space here. Some coefficients, don't pay attention to them. You have to subtract some polynomials up to order w, and then add some arbitrary polynomial here. But this subtraction depends on the phi I itself. And these constants are arbitrary. So this is your general solution to the extension problem. Now if you want to have some particular solution to your extension problem, then you may require that your extension has some number of derivatives up to order omega, actually you can have them, equal to 0 at some arbitrary point. This would be the normalization point actually in usual quantum field theory. So you pick up some momentum q, and you require that all the derivatives with respect to k at this point of q up to order omega vanish. And you can easily do this because you have at your disposal arbitrary coefficient ca, and the number of these coefficients is sufficient necessary and sufficient to do all these requirements. If you pick up this particular solution for your problem, then this auxiliary function w, which was everywhere here, that completely disappears from the solution. And now you have this nice solution to the extension problem, which involves only your original distribution and its derivatives at the point q with up to w. So of course we have to assume that the derivatives exist at this point q. So we have to pick a point q where they exist, but it's not very difficult. usually Fourier transform of distributions encountered in quantum field theory are smooth functions in a large amount of space. Somewhere they may be singular, but they are regular in.
Physically, what's the physics behind those arbitrary?
Now, that's next slide. Now, I want to stop here a little bit because this is just what we arrived at is the momentum subtraction scheme in the usual quantum field theory. What you see here is the distribution. If I remove this chi sub a and replace here something like Feynman propagated to the power of n, it is completely ill-defined. Yes, but this multiplication, you can think of it as a regularization of your ill-defined distribution. So suppose in some way you have regularized your Feynman propagated to the power of n, and you substituted it here. So all you have to do is subtract some polynomial from your regularization. This particular polynomial, take particular derivatives at point q times k minus q to the power of a after you subtracted it. So now originally if you remove regularization you arrive at an infinite expression again, right? You regularize something, then you remove regularization, you get infinite result. Now if you make a number of subtractions and then take the limit, then you get a finite answer. So that's how actually the MOM subtraction scheme works in quantum field theory. But here it is justified because we did not have to, cope with some infinities which we have encountered in quantum field theory. We just extended distributions. They gave you finite answers, and this is the finite answers that they give from the very beginning.
That seems to be suggesting that momentum subtractions are somehow better. Somehow you seem to be motivated ahead of, say, I don't know, dim reg or something like that.
You see, no, maybe it's because, you see, I've chosen a particular way of extension of a distribution, which,
They were unique.
well, the extension is unique, but the particular way of calculating it, maybe not unique. I know only this way of doing this. Yes, by the way, in the book by Scharf, you will find completely different method, completely different.
That might give you something now.
I think it's more complicated and it's hard to see. Well, some things will be similar, some things will be no, sorry, in the book you'll find similar method. In some other papers you may find some completely different methods. So the point is you solve a mathematical problem, but you can solve it probably in different ways. How do you explicitly find an extension? Here I multiply it by some function chi, then take a limit. Maybe you can invent some other procedure which would be more wise or different or whatever. And there are such procedures actually in the literature. Yes, at least one paper I know. So this looks similar to momentum subtraction scheme. Others maybe look similar to some other schemes.
But dim-reg is also a way to define such products and distributions, right? Because in
Dimensional regularization.
you can say that.
We should talk about this because
First do Fourier transform of that divergent distribution. The Fourier transform diverges, and there is a pole, and you just subtract the pole.
So the question would be how to make a parallel here with the dimensional regularization, because I don't want to deal with infinities from the very beginning. I want to deal with finite functions all the time. So I want to find a finite extension by using perhaps method of dimensional regularization. That's a good question to ask. But it's only a method of solving mathematical problem. I want to stress this point here. It's not a method of struggling with infinities which were encountered by your ill-defined calculations.
Excuse me.
Yeah.
This is the last formula. You have still arbitrary coefficients.
Absolutely, yes, absolutely. No.
Okay, but the previous formula again arbitrary CA.
Yeah, these are different CAs actually, because these CAs are arbitrary and these CAs are also arbitrary. So my general extension problem is some particular extension plus this polynomial. In coordinate space is just sum of derivatives of delta function with coefficients. In Fourier space it's a polynomial in K.
Okay, but as far as I understand, you reduce in some sense CA to go to this last form?
I use CA to find out some particular partial solution of this. So from this general solution to the problem, I picked out a particular one, and it is now here, this particular one. But the general solution is a particular one plus another arbitrary polynomial. So this is another arbitrary polynomial. It's not; these are not the same C's. These are different C's, but because they are arbitrary, they're, there and there. I may not be able to. Okay. So how it works, step by step. So, like, first of all, we are looking for the coefficient standing in front of monomials of this kind, or whatever. Yeah. Phi to 4. There is unity standing here. It's single order is -4. It is completely uniquely extendable and extendable to unity, of course. It's not interesting. Now the next graph is like this. So it's symbolic graph now, right? So the distribution to be extended is this one. So it's theta plus times d to the power 1 power of 1, minus theta minus d minus power of 1. Now this function has w equals to -2. It is uniquely extendable again to 0 because w is less than 0, and its extension is precisely Feynman propagator. So it's a general property that the tree graphs become usual quantum field theory tree graphs. They don't involve any ultraviolet divergences, and they of course are unique here. Okay. Now the next function is something that uses two contractions of fields. All right. So you have phi squared now. Phi squared here remaining. But the two contractions took place, and these two contractions now look like a distribution of this kind. D plus squared, D minus squared. Up to now it's a fine distribution. We have to extend it to 0. Now we use the procedure that was explained actually. You regularize it or multiply by this chi, this thing, take Fourier transform, then make a subtraction. How many subtractions we have to make? Only one, because w equal to 0. So under the Fourier integral, we make one subtraction, and you see that you know that this originally divergent integral becomes convergent after one subtraction at a arbitrary point q. See, becomes convergent and gives you the result, which the textbook results for the term standing in front of this. So this is the result. Q is our normalization point, which can be taken to be arbitrary. For example, can be taken to be 0 in this case. If mass is not equal to 0, then Q squared can be taken to 0. Well, now, but this.
Obviously, that you'll get when you talk about mass renormalizations, then they're going to go like.
But this is this is. Excuse me.
I know you're not doing that here, but isn't it? Because it seems like this Q is just completely analogous to the momentum, the arbitrary momentum scale you put in. So presumably, if you did the calculation of how the corrections to the mass, it's just going to go like actually Q squared would be the same thing. I'm guessing.
Let's go to the mass point first. This contributes to the scattering. It's not related to the mass, right? Now the general solution is of course our particular solution normalized at Q plus some constants C. Omega is equal to 1. We have only one integration constant. Where it enters some the contribution to the scattering operator corresponding to the C. You can see it through this line of reasoning. It just renormalizes the coupling constant lambda here, right? So it's something which you have added up a finite constant which shifted your lambda to a finite step, in a finite step. Well, if you want, you can just say that your lambda is not renormalized at this point Q, and therefore you'll get no renormalization of lambda at the point Q. So I stress these normalizations are present here, but they are finite. They are not infinite. The next thing would be the mass term here. So the mass term would involve cubes here, right? So now the W of this distribution is equal to 2. You have to make 3 subtractions before, in this Fourier space, yes, before you integrate. So after you make 3 subtractions, your divergent integral becomes convergent, and it gives you some result, very complicated result. It's calculated only in a few books, maybe, and not even completely. It's a complicated calculation, but it's a finite calculation. The general solution is this finite result plus C0 plus C2 times k squared. This is written down from the reasoning of Lorentz invariance, of course. So we should import. Our solution should be also Lorentz invariant. Yeah. So we have basically only 2 constants here, not several of them. And now you can see what these constants do. They renormalize. One of them introduces the mass term here, right? In the scattering operator, additional mass term. Another, you can say that it renormalizes the wave function, right? But you can also safely say that they do nothing. So you can safely evaluate them to 0 by saying that your mass in your original Lagrangian and the wave function are the physical ones. They don't have any contribution from your renormalization scheme. This is perfectly correct to do. The vacuum graphs are very divergent, but they actually have to be, well, they can prove to be actually equal to 0 if you require that they are finite in the so-called adiabatic limit. Adiabatic limit means that your test function is switched on to unity everywhere. I will not dwell perhaps on this point. If you have a discussion, I can answer you. Now, actually, if you consider some physical processes, for example, you take this operator T3, which is responsible for the just propagation of a particle, right? And you require that this thing, yes, in the scattering operator has valid adiabatic limit. I should stress again that once your switching function, the function which switches interaction, when it is it has compact support, for example, yes, vanishes somewhere, yeah. So the scattering operator corresponding to this diagram is always finite. Always finite. But you want to make an adiabatic limit. You want to switch your interaction in the whole of space. Gradually you want your G to tend to unity everywhere. So this limit does not always exist. In this particular case, in order that this limit exists, you actually have to demand that your mass and the wave function are equal to the observable ones. In other words, that this T3 should be normalized to 0 at the point where Q squared equal to mass squared. That's what I'm going to say. Otherwise, this thing would diverge in the adiabatic limit. So this is one of the reasons, one of the kind of effects of this theory, which by itself requires the non-renormalization of mass and wave function. This happens in this scalar theory, in the quantum electrodynamics as well. Mass of the electron should not be renormalized if you want the adiabatic limit to exist.
So you're saying if I had a light scalar and a heavy scalar and they were coupled, I wouldn't get that heavy scalar renormalized to mass of the
A light scalar.
A light scalar and a heavy scalar.
Yeah, but you will have.
Simple model where I have two scalars in the.
Oh, you mean there will be some mixture of them or something? Is it? Yeah.
So you look in standard QFT calculation.
Yeah, I see. That I don't know, but something similar should be there. I mean, something similar should happen.
Because that is the mass hierarchy.
Yeah. No, you see, well, I think the same would happen in that case as well. So you have one field with mass m1, another with m2, right?
So I wouldn't say that. Okay, the same thing happens, and there's no there's no solution.
But I guess this would happen. But I have not done this. But I guess this would happen. You mean there's no solution? Well, we have to think. Yeah. Okay. Time is over. Now I think I've said more or less. So this term is finite in the adiabatic limit. There is nothing to do with this scattering amplitude. And again, I mentioned there is a recursive solution which allows you to find T of xn recursively by using the same causal property, and the same extension of distribution that we used before. Renormalizability of lambda 4 here means that the W which you encounter, the singular order of distributions which you encounter in your construction, do not depend on the order of perturbation theory. They are limited here. It's 4 minus number of external lines. It's the usual degree of divergence in quantum field theory. In this sense, you don't have to add more and more constant C. So the number of constant C is finite. They are normalized mass, coupling, and wave function. And these are my conclusive remarks. So perturbative QFT is quantum theory of distributions from this viewpoint, right? Can be regarded as a system with infinitely many degrees of freedom, but you can take another viewpoint, as it's a distribution which you are quantizing, which is important. So here, renormalization does appear, but it arises in the extension of distribution and does not involve any infinities intrinsically, at least mathematically. So the issues of, well, this probably removes some issues which people think are important. Some people think they are not, but many people think they are important in quantum field theory, like naturalness or mass hierarchy. Okay.
Particles are sitting above a certain mass scale. You kind of have to assume they are there. So they correctly.
So that's maybe the final remark is that, well, of course we know that all our physical theories are approximate. So whatever theory you take, you know, it has some limited validity, etc. But mathematically, many of our theories are perfectly well defined if you don't think about their limits, right? Like GR, perhaps I can give you an example, or Newtonian mechanics. Yes, it's perfectly well defined mathematically. You can set up initial value problem and solve equations. You don't run into any inconsistencies, etc. So perhaps, of course, we know that QFT probably is not complete, but at least it's maybe important to have a mathematically complete theory, self-consistent in a mathematical way, although incomplete in a physical way. Previously, we always thought that it's impossible somehow, right? So every version of QFT which is physical is also mathematically incomplete. It runs into infinities, and these problems were always related to physics, rather than to mathematics. So here perhaps is an example of another way of reasoning, when the problems which you encountered may be traced to purely mathematical errors in some sense, which you make by forgetting the nature of the objects you're dealing with. So an object is a distribution. You quantize the distribution. Thank you. I'm sorry.
You still run with scale,
Excuse me.
the parameters you get, your coupling constants, they're still scale dependent, although you set these things.
Well, in some sense, here all the usual phenomena like scale dependence, running coupling constants, you can have them here as well. Yeah, because your lambda is dependent on momentum, and you can effective lambda now, because scattering amplitude now is not just lambda, but something momentum dependent. It's a complicated expression. It was presented there. It depends on momentum. You can ask very similar questions: how it runs with increasing momentum. You can write down these Renormal group equations. Perturbative, of course, all this in the sense of perturbative quantum field theory.
You can do 5 to the 6 with that. Can you do that as well?
Pardon me?
5 to the 6 would be normally normalized. You do
if your theory is 5 to 6, yeah, then it would generate, this method would generate you higher order terms, 5 to
So it'll be finite.
8, and sorry,
It'll all be finite.
they'll all be finite. That's true, yeah.
They all depend on that, on these arbitrary scales.
And so you'll have an emergent of coupling constants, all of them finite, but they will have to be specified by you, by an experimentalist, but they will be finite, right? But there will be infinitely many of them. Each order would generate next series of such coupling constants. Nothing different from the usual QFT in this respect. I mean.
We have to stop.